So having completed the recent exercise, which gives us some properties of radicals of ideals, we are next going to see this another property of radicals. The radical of an ideal I equals the intersection of those prime ideals in the ring which contain I inside of them. So let's see the proof next. The proof starts by recalling something which we saw immediately after defining the radical of an ideal, namely this equation. Do you recall this equation? We saw earlier that R of I equals the inverse image of RA/I under phi. I is an ideal in the ring A. That is already there in the background. And RA/I is the set of all nilpotent elements in the ring A/I. It is the nil radical in A/I. We already know that it's an ideal. And what is phi? Phi is the natural homomorphism of A onto A/I. So that's how we have this relation. Alright, so let's just keep it here. Now let omega denote the set of all prime ideals of this quotient ring A/I. Then you recall how we can express the nil radical in terms of the prime ideals of the ring, because this is the nil radical of the ring A/I. Proposition 1.8 tells us that it equals the intersection of all the prime ideals of the ring A/I. And the collection of those prime ideals is omega, so it equals the intersection of all j's which are coming from omega. So now next what you are going to do, next you take the inverse image on both sides under phi, under the map phi. Now you know that inverse images behave very well with everything. In particular, the inverse image of an intersection is equal to the intersection of inverse images. So that's how we are going to get something next. Let's see. Okay, so accordingly we have this, the inverse image of RA/I under phi equals the intersection of the inverse images of all the elements in omega. Now let us recall a result. Result means an observation way back in these things about prime ideals related to homomorphisms. Say you have two rings A and B and there is a homomorphism F from A to B, and you take a prime ideal in B, then its inverse image under F will be a prime ideal in A. So that means if we now take any J from omega, then what is J basically? J is a prime ideal of this ring A/I. Do we have a homomorphism in the picture? Yeah, of course. This phi. This phi is the homomorphism from A to A/I, and we are taking a prime ideal J in A/I. So its inverse image under phi is going to be a prime ideal in A. But we also, of course, already know that it's going to contain I, because our homomorphism phi is a homomorphism of A onto A/I. That is why. So where are we now with all these things? What is our actual thing that we want to prove? We want to prove that the radical of I equals the intersection of all prime ideals of A containing I. Because of this equation, we see that instead of considering the radical, we can consider this and work with this, which is what we are doing. And in this equation, we seem to have been able to express this as the intersection of some objects. And just now we have seen that these objects are prime ideals of A containing I. Some prime ideals of A containing I. However, we want all prime ideals of A containing I. If we can show that, then this combined with this will give us our claim. Now next what we are going to do is that if we consider any prime ideal of A containing I, we are going to show that it is going to appear like this, phi inverse of something from omega, and then our job will be done. So let's go for that next. So let P be a prime ideal of A containing I. Now we want to prove that P is going to appear as phi inverse of J for some J coming from omega. So let's see how we can do that. The first observation we have is this. Since P is non-empty, being an ideal of A, P is a non-empty set, a subset. So its direct image under phi would also be non-empty. Phi of P would be non-empty. And where will phi of P lie? Phi of P will lie in the ring A slash I, because phi is a mapping from A to A slash I. So phi of P is now a non-empty subset of this quotient ring. In the first part of this argument, we want to prove that phi of P is an ideal of A slash I. And accordingly what we do, what do we need to show that phi of P is an ideal? First of all, it has to be a non-empty subset of A slash I, which we have. Then it should be closed under the formation of difference. If you take any two elements from phi of P, their difference should belong to phi of P. That would tell you that it's a subgroup of A slash I under addition. And then when you multiply any element of phi of P by any arbitrary ring element from here, the product should belong to phi of P. Then it will be an ideal. Because of the nature of phi of P, choosing two elements in phi of P is equivalent to choosing after all two elements in P. And you just have to consider their phi images. Okay, and those two elements are pi 1 and pi 2. If this looks weird, you can just write P1 and P2. Along with these things, we also choose one element A from A. Okay. So then what do we see? What can we do with these things? Notice this difference. Phi of pi 1 minus phi of pi 2. So this is the difference of any two elements in phi of P, because that's how they are going to look. Because phi is a homomorphism, this will be equal to phi of pi 1 minus pi 2. Now pi 1 and pi 2 are coming from P, so their difference belongs to P. And that is why the phi image of this difference belongs to the phi image of P. This proves that the difference of any two elements of phi of P is again in phi of P. So phi of P is the legitimate subgroup of A slash I under addition. Next, we consider this product phi of A times phi of pi 1. So this is any element of phi of P, and this is any element of A slash I. Why is this any element? Do not forget that phi is an onto function from A to A slash I. So anything you choose from A slash I is going to look like phi of something from A. That is why we chose A from A. So by writing phi of A here, you are not losing any generality. This is really how any element of A slash I looks. And you actually know what this element is. It is the coset A plus I. But anyway, we don't need that. So this product, because phi is a homomorphism and so would respect multiplication, this product would be equal to phi of A pi 1. Now note that P is already an ideal in A and A is an element in A, pi 1 is an element in P. So A pi 1 belongs to P. So the phi image of A pi 1 belongs to the phi image of P. And that is why phi of P is an ideal of A slash I. But we are not happy with simply having an ideal. We want it to be a prime ideal. So next we go for that. But for the ideal to be prime ideal, before you go to the condition for primality, you need to make sure that it's a proper ideal. It should not be equal to the entire ring. What will go wrong if it is equal to the entire ring? Suppose we forcefully suppose that phi of P equals A slash I. Then among the many elements that A slash I has, this one is also there, the identity element, 1 plus I. That has to belong to phi of P. So that will be equal to something, some element from phi of p, which will look like this, phi of pi for some pi belonging to p, but this is just pi plus I. So if these two cosets are equal, you know from the condition when two cosets are equal, if you take their difference of their representatives, in this case which are 1 and pi, then that difference belongs to the ideal whose coset you are considering. So that way 1 minus pi belongs to I. But P is a prime ideal of A containing I. P contains I inside of it. So if 1 minus pi belongs to I, 1 minus pi has to belong to P. But already pi belongs to P. So if you take the sum of 1 minus pi and pi, that has to belong to P, which however is 1. So 1 has to belong to P. That however is a problem. 1 cannot belong to P, because when an ideal has the identity element, it equals the whole ring. Whole ring in this case would be A. But what would go wrong from that? Namely the fact that P is the prime ideal of A, and so by definition a proper ideal of A. P cannot be equal to A. So that is why this supposition would be wrong. So next we are going to write that. Okay, so we continue from here, but then A is equal to P, which is a contradiction. Now you know why, because P is a prime ideal. So our supposition is wrong, i.e. phi of P is not equal to A. So now we have additionally established that phi of P, besides being an ideal, is the proper ideal. Now we can go for the condition for primality, which is what? Which is this. If you take any two elements from this ring such that their product belongs to phi of P, and then at least one of them belongs to phi of P, if you can show this, if this is true, then phi of P would be a prime ideal of A slash I. So any two elements of A slash I means what? Those elements are going to be phi of something. So we start by taking any two elements in A such that the product of their phi images belongs to phi of P. But what does that mean? I mean, what does that give us? It gives us this, that phi of AB belongs to phi of P. And so phi of AB is going to look like this, phi image of something, some P from P. And then what do we get from that? Alright, so now if we really write what these phi images are, then in place of phi of AB, you have AB plus I, and in place of phi of P, you have P plus I. So again, as before, AB minus P then belongs to I, and since I is contained in the ideal P, so AB minus P belongs to P. But P is already in P, so that's how you get AB in P. Now A and B are two elements of A in which P is the prime ideal, so that their product AB, now you can see that it belongs to P. So since P is prime, either A belongs to P or B belongs to P. But then either phi of A belongs to phi of P or phi of B belongs to phi of P. So this condition has led to this. So that means phi of P is really a prime ideal in the ring A slash I. So we write that, thus phi of P is prime, it's the prime ideal in A slash I. Now you already have this containment from simple function theory, that P is always contained in phi inverse of phi of P. It's very easy to see why this is true. You take any element of P, calculate its phi image, obviously that is in phi of P. So that element by definition of inverse image would be contained in the inverse image of phi of P. That's it. So this is always true, but we want the reverse inclusion to be true as well. For that, what we do, we take any element X here. That what does it mean for X to be in this inverse image? that phi of x would belong to this set, phi of p. So that means again same thing as before. We have already gone through this type of argument 2 times in this proof. So phi of x equals phi of p prime for some p prime belonging to p. Phi of x is x plus I, phi of p prime is p prime plus I. So then x, these two are equal means x minus p prime belongs to I. Again you use the fact that I is contained in p, and that is why x minus p prime belongs to p. But p prime is already in p, so x belongs to p. So any element x here is here as well. So you have the reverse inclusion as well, which means now you have equality. Okay, so we write equality, and then we also note the fact that phi of p is in omega. We could have written this before, but this is where we actually need it, so that's why I am writing it here. And the proof ends here. Why? Because we already saw that this is the case. We were able to express this inverse image and hence the radical of I as the intersection of some prime ideals of A containing I. And we were worried about whether all prime ideals of A containing I are appearing here in this intersection or not. So accordingly, we took P as a prime ideal, any prime ideal of A containing I. And what do you see now here? That P really looks like phi inverse of something. And what is that something? That something is coming from omega. So yes, in this intersection itself, all prime ideals of A containing I have been accounted for. So that is why the proof is over. And let me end this video here itself. Besides this property, there are 2 other properties in this section, I can say. So next week we are going to see them and their proofs. And after that only we can go to extension and contraction of ideals, with which this chapter is going to end. So see you next week on the same day with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.